All right, so I want to do one problem from 162, and then we'll go on to a new topic. Okay, so this is still from 162 volumes. All right, so here's the question. We want to find the volume. That's under the plane z equal minus y plus 5, and above the triangle in the xy plane with the following vertices. Okay, so we have 0, 0, 2, 2, 6, 0. Okay, so what we do is start with drawing this triangle in the xy plane. All right, so in that way, that's how you figure out the order of integration and what the limits of integration are. So we're going to just put these points on 0, 0, and then 2, 2 here, and then 6. Okay, here, 6, 0. So here's our triangle. Maybe I'll do it in another color. Okay, so that's the triangle in the xy plane. And we're going to integrate over this, okay, and under this. So if we call this, let's say A, all right, for A for area, you can represent our integral as follows. We want to integrate over that region A, and here you can write, this is one way of representing it, then you can write dA, okay, which means dx, dy, or dy, dx, depending on what we decide. Okay, so this is one way of writing this. This is called a double integral. And once we put on our limits of integration, that will be called an iterated integral. So now let's decide on the limits of integration and whether or not this dA is going to be either dx dy or dy dx. Okay, so now let's decide on the limits of integration. Now let's suppose we decide to do y first. If we do y first, well, y goes from, it hits this top line, and it hits the x-axis. That's if we're to the left of 2. But if we're to the right of 2, then it hits another line, and it hits the y-axis. So if we were to do dy first, we'd have to do 2 integrals, split it at 2, all right, and have 2 separate integrals. So we don't want to do that. We don't want to split the integral. So everyone sees what the problem is with dy first, because we have, when you draw these arrows going from the bottom to the top hits at 2 different lines. So we don't want to do dy first. So let me get rid of those arrows. Okay, so we would rather go this way. And that's the x direction. So x can go from this line to this line throughout A. All right, we won't have to split it up if we do dx first. So that's what we're going to choose to do. So let's write our equations for these lines. This is the line y equal x. This one here is y equal x. We can see the slope is 1 and it goes through 0, 0. This one, let's look at the slope. Okay, this is above 2 here. Let's look at the slope. If we go from this point to this point, we're going to go down 2 and 1, 2, 3, 4 and right 4. Okay, so that's minus 2 over 4. Minus 2 over 4, or slope minus 1/2. Now we just have to decide on B. All right, so we can do that by just substituting in the point. Like, let's suppose we substitute in the point, let's say 6, 0. Okay, so that would be x equals 6, y equals 0. Here, I'll just do the little calculation over here. So 6, 0 is on the line, so we can substitute in 6 here and 0 here. Okay, minus 6 over 2, that's minus 3. So we see b is equal to 3. Okay, so I'll put a 3 here. So now we have the equation of our lines. All right, but we want to get the equation in terms of x. All right, well, we know x equal y. We want to solve for x. Okay, here that's easy, x equal y. And here we want to solve for x because we want to integrate first, we said, with respect to x, all right? And because that way we won't have to split up our integral. So we're going to do dx dy, not dy dx. Okay, all right, so I want x equal. All right, so let's just solve this. We're just going to solve it for x. All right, I'll put the 1/2 x on this side, and there we have minus y plus 3, and then multiply both sides by 2. So we have minus 2y plus 6. All right, so that's what that is. All right, so since we're doing x limit of integration, we need these to be solved for x. X equal y on this side, and x equal minus 2y plus 6 on this side. So x is going from left to right. So left, we have x equal y. Right, we have x equal minus 2y plus 6. So those are our limits of integration. Now, the second set has to be only numbers. All right, so y is going to go from whatever the lowest point is to the highest point. So 0 up to 2. Okay, from here to here. That's the greatest distance there. So it's from 0 to 2. Okay, so that's our dy. Any questions about that? So this one's called the iterated integral. All right, and now we just start evaluating. So step 1 is we're going to integrate with respect to x. Okay, x is a variable, so minus yx, y is like a constant, minus yx plus 5x. Okay, so we integrate like that, and now we're going to substitute in for x. Okay, because x is our variable, so we're substituting in for x, minus 2y plus 6. And after we do that, we'll have only y's in our integrand. So let's start that substituting. Okay, so we have substitute for x minus y minus 2y plus 6 plus 5 minus 2y plus 6. Okay, and now we have to substitute in y. Okay, so that's minus. Substitute in y here, we have minus y squared. And substitute in y here, and we have 5y. Okay, so we have all that. Okay, we have all this, and now just start simplifying this. Okay, so here we have 2y squared minus 6y, I'm opening parentheses, minus 10y 5 times 6 plus 30. Okay, negative, open these parentheses, minus minus y squared plus y squared. And then finally minus 5y dy. Okay, we have some like terms. Okay, here, 2y squared, 3y squared. And minus 6y minus 10y minus 5y. Okay, so we have minus 16 minus 21y. And then we just have plus 30. Okay, so integrate the usual way. Okay, so this would be y cubed over 3. So here we just have y cubed minus 21y squared over 2 plus 30y and 0, 2. Okay, so why do we have minus y squared plus 5y? Okay, here we substitute in this. We're substituting for x here and here. And now minus, we substitute for y. We substitute y. First we substitute this. Okay, that's this part. Minus, substitute y. So when we substitute y, we get minus y squared. We get this. Plus 5y. Okay? Is that clear? Okay. So we're substituting for x. First this one, then this one. All right, so that's the second one is right here. Okay. All right, and then we did a lot of simplifying. Okay, yeah, let's explain again about the limit. So that's the complicated part here, really, is the limit. So let's go up. Okay, so Elizaveta asked about explaining about the limit, so let's do that. Okay, so that's why it's important to draw this picture, draw the triangle. Then we have to figure out these lines. The equation of this line is y equal x. The equation of this line, well, we got the slope, okay, down to right for minus 1/2. Then substitute it in the point to get this value 3. Okay, so that's y equal minus 1/2 x plus 3. Okay, we got the slope and we got the y-intercept. But then we decided we can't integrate first with respect to y, because then we would need two integrals, because y goes from the x-axis to the first line if we're here, but if we're to the right of 2, it goes from the x-axis to a different line. So the top, if we do dy first, then we have to split it up into two integrals. But if we do dx first, x goes from the left, from this line to this line throughout. Okay, if you keep drawing these blue horizontal lines, the left hits y equal x, the right hits y equal minus 1/2 x plus 3. Okay, so it makes sense to do dx first. Okay, and then we do left, right. Left is smaller than right in the x direction. Left is smaller. So left, we would have, this is the equation x equal y. Solve for x equal y. So x is equal to y on the left. And on the right, it's equal to, we solve for x minus 2y plus 6. That's on the right. So this is left, right. Okay, and then y, here we have numbers. Okay, so y goes from the lowest point, which is y equals 0, to the highest y equal 2. Here's 0 to 2 on the y-axis, 0 to 2. So that's y. Okay, do you understand that? The limits of integration? And then we, okay, so we decided we're doing dx dy, so now we have to integrate with respect to x. All right, so these are like constants. So for the first term, we get minus yx, and the second term, 5x. Then we have to substitute these in for x, because we're integrating with respect to x. So you put that here and here, minus and then you put y in for x. Okay, okay, how do we get minus 1/2 x plus 3? Okay, let's see that. Okay, how do we get this line? So basically, what we do is y equal mx plus b. Okay, here, let's look at that. We had 2, 2, and 6, 0. Okay, let's look at that separately. Okay, so we're looking at the equation of the line from 2, 2 to 6, 0. Okay, so 1, 2, 3, 4, 5, 6. Okay. So we find the equation of the line, y equal mx plus b, using that. Now, to figure out m, we have, you can just do the slope formula. Okay, so we can just subtract y's, 2 minus 0, and then subtract x's, 2 minus 6, we have minus 4, so that's where we get the minus 1/2. So we have y equal minus 1/2 x plus b. All right, and now figure out b by substituting in 6, 0. All right, so that's 0 for x, 6 for y, sorry, 6 for x, and that's 0 for y. So here we have minus 6 over 2, minus 3. Okay, so that's how we got b equal 3. All right, so we have y equal minus 1/2 x plus 3. So we got a 3 here. Okay. All right, so that's our line. But we're going in the, we want to know where x hits on the left and where x hits on the right. So we need to solve for x. X equal y, y on the left, put that at the bottom. And here we solve this one for x. And so x hits on the right at minus 2y plus 6, so that goes on top. Okay, and now the y limits of integration, I said only numbers for the outer one. All right, so y goes from the lowest point 0 in this triangle, the lowest y value in this triangle is 0, up to the highest y value is 2. So it goes from 0 to 2. Okay. Is that clear? How we got the limits now? Any questions about how we got those limits? Okay, so we were busy substituting in for x. First this, minus, substitute in this. So that's all that. And we have to simplify, okay, like terms, and then finally we get this. And finally we're up to the last stage where we substitute in. First 2, we have 8, minus 21 times 4 over 2, plus 30 times 2, that's 60. And substitute in 0, we get 0. Okay, this is 2. Okay. So we have 8, and then we have minus 42 plus 60. Okay, so that's 8 plus 18. 8 plus 18, so we have 26. Okay, and that's our volume. Okay, any questions? So this I consider to be a reasonable problem. All right, not too hard to integrate. The most difficult part really is those limits of integration. Okay, setting up the triangle and the limits of integration. Okay, so any questions about how we did this? All right, so you should go over this example and the other ones that we did. Okay. I'd say the two types of examples you're likely to come across is something like this, where we're integrating under a plane. When you integrate under a plane, the function that the f of xy is usually quite simple. So the integration is very doable. So that's one type. And another reasonable one that's more difficult would be something like we did last time, where we integrate underneath the parabola x squared plus y squared. All right, so one of that type. Okay. Okay, any questions before we go on? All right, so we're going to start the last segment of the course, although like I mentioned before, there are two optional sections that I would like to come back to. In the previous segment, I'd like to talk about the gradient and directional derivatives. That's, in the section on differentiating a function of two variables, partial derivatives. Okay, so I would like to get back to that, and I think we will have time, I'm pretty sure. But for now, we're going to go ahead and we're going to do the last segment of the course, which brings us back to we're going to go back to really one variable, functions of one variable. And what we're going to lead up to, all right, so far we're going to start slow, but what we're going to lead up to is some functions like can be approximated by infinite polynomials. Like, for example, polynomials are easy functions to work with because we can just figure out what they are by substituting in a value. But if you have something like e to the x, for example, the only way we know what e squared is equal to, let's say, is by using our calculator, because we don't have an equation for e to the x. It's not a polynomial. But we will see that e to the x is equal to a polynomial that's infinite. All right, so e to the x is equal to 1 plus x plus x squared. We'll see it over 2. We'll see this, later on in the course. An infinite polynomial. This is the simplest one, really. These are factorials, and it goes on forever. So this is basically similar to a polynomial. It's just an infinite polynomial. And now if we want to figure out what e squared is, we can start substituting in the 2 here, keep going, and we don't have to, obviously we can't figure it out exactly, but we can use, let's say we decide to use this many terms, 1, 2, 3, 4, 5 terms, and that will be our approximation. All right, so that's what we're leading up to. And these sums that are infinite, those are called series. So a series is an infinite sum. So first we're going to talk about what we call sequences and series. So I'm combining two chapters, 101, 102. This particular series contains a variable x. The series that we're going to start talking about will not contain variables. It'll just be an infinite sum of numbers. Okay. All right, so now that you know where we're heading, we're going to be approximating functions of one variable, functions that can't be written as a polynomial. We're going to be approximating them as an infinite series or an infinite polynomial. All right. Okay. So first we'll talk about a sequence. A sequence would be the individual terms not added. And then we'll talk about series. So a sequence can be represented by brackets with a sub n, or this represents a list of numbers. A list of numbers going on forever. So that's called a sequence. It's just an infinite list, basically. So I'll give you some examples. Sometimes very often they form a pattern. So here's an example. We'll just the whole numbers. That's a sequence, and the general term you could say would be n, like that. Okay. Or even numbers, and the general term would be 2n. That's like the general way of representing an even number. So just some examples of sequences. Okay, here's another one. Here's some fractions, and you see what the pattern is. Just 1 over n. Okay, we keep increasing this by 1. So that's the general term, the nth term, or 1 over n. All right, now this one, in this case, let's say we call this, this would be the general term. We'll call it a over n. This is a over n. And here, this one, in this case, this one's a over n. And one thing that's different about number 3 is that a over n keeps getting smaller and smaller. These fractions keep getting smaller. So we could say a to the n goes to 0. Or more precisely, the limit as n goes to infinity of a to the n equals 0. Okay. As n gets larger and larger, 1 over n gets closer and closer to 0. And here's another one that also has a limit. Does someone want to tell me what the limit is? Let me just write with the general term, or let's also talk about the general term. What's the pattern here? Well, right, that's right, the limit is 1. That's good. Okay, great. So these are getting bigger and bigger, but they're not getting beyond 1. The limit is 1. If we look at this pattern, the top is smaller than the bottom, 1 smaller than the bottom. So we could call the top n and the bottom n plus 1. That could be the general term. So that's our a to the n here. Right, and like you said, a to the n goes to 1. Okay, let's look at one more. What's the general term here? What's the pattern? Okay, I think you wrote n squared. I think you mixed those up. I think you meant put the 2 first, and that would be right. 2 to the n. Okay, right, like that. Okay. So basically, we keep multiplying by a half. So here you have a half. Multiply by a half, and you get 1/4. Multiply by a half again, and you keep going. So you keep on multiplying by half. By the time you get up to here, you multiply by 1/2 n times. Okay. So here also, let's call this a to the n. We also have, well, not going to 1, but this time it goes to 0. This starts getting small very quickly. So these terms, this go to 0. Well, anyway, we spoke about, I wrote down a limit, but we didn't really define what the limit is. So we'll just say the limit as n goes to infinity of a to the n equal L if a to the n gets arbitrarily close to L as n goes to infinity. All right, this is like the approximate definition, or the, and this is the type of definition that we used to define a limit when in Math 15, like the limit of a function. Okay, it's not a precise definition because we're not writing exactly what arbitrarily close means as n goes to infinity. We're not really writing what that means exactly. I'll give you the more precise definition as well. All right, like you could say, let's say you challenge this word arbitrarily close. Just to give you the precise definition, before I give you the precise definition, just imagine if you told somebody that the limit is L, and because a to the n gets arbitrarily close to L as n goes to infinity, and they say, well, can you get it within 0.1 of L, within 0.1 as n goes to infinity? So can you get it to stay within 0.1? Or let's say you're talking about, let's say you're talking about a machine that's producing something that has a precise measurement, and you're being challenged. You manufacture the machine, and you're saying, well, can you get it within 0.1? If we let's say it depends on how precise the machine is. Maybe depends on, let's suppose, the amount of money that you spend to develop the machine. Let's say the more money you spend, the better it is. So our n would be the amount of money that you spend. Okay, as n goes to infinity, the machine becomes more precise. So that's the situation. So you tell somebody, well, if I spend, let's say, $1,000 on the machine, then I can get it within 0.1 of our measurement. I can get it to be accurate within 0.1. So, okay, so that's like the challenge. And let's say somebody says, well, can you get it within 0.01? And you say, well, if I spend $5,000, I can get it within 0.01. All right. Now with that in mind, okay, let me show you the precise definition. So here it goes. It's good to see this definition once and just understand it. Okay, so here's the precise definition. And let me explain it to you in terms of that example of a machine and spending a certain amount of money to get it to be precise. All right, so epsilon is like our 0.1 or our 0.01. Epsilon is a small number, and that could be how good our machine is, how precise it is. M is the amount of money that we spend. Okay, so if epsilon, let's say, is 0.1, okay, then the M would be, in our situation, let's say $1,000. So if we spend $1,000, then we can get the machine to be, here's the precise measurement. Here are the measurements that we're producing. Okay, so we can get the measurement that we produce by the machine and the precise measurement the difference can be less than 0.1 if we spend $1,000. If we spend $1,000, we can get it less than 0.1. All right. So this little n means how much we spend. So a sub 1,000 should be, when we subtract, should be less than 0.1. Certainly a sub 2,000, if we spend more, will also be within 0.1. Okay, so you understand this definition in terms of that example that I gave. So epsilon is how precise, m is the amount of money you have to spend, and if you spend more, anything more over 1,000 is going to give you your precision that you want. Okay, so that's the more abstract definition, or actually, let's say the more precise definition, but the concept's a little bit abstract. Okay, because what's epsilon, what's m, like what are we talking about? But I think if you think of it in terms of a real life example, it's more understandable. So I just wanted you to see that type of definition. All right. So what we're going to do now is a few problems. We're going to ask, or let's just say, there's just one more vocabulary word that I think you're familiar with. Okay, so if a to the n goes to some limit, then we say it converges. Okay, if not, then it diverges. So just vocabulary. Okay, so we're going to do some problems where we ask, does it converge, converges, or diverges? And we'll just have a couple of methods for figuring this out. So we'll have the nth term, and we'll want to know if it converges or diverges. Okay, so here's one example. Let me make it 3n squared. Okay, so we want to know, does this converge or diverge, or what's the limit as n goes to infinity? So this one we can do as follows. This was like the problems that we did in the past when we figured out what we called end behavior of a function. What happens when these get large? So what you could do, here's one method. If you have a polynomial over a polynomial, then one method would be divide top and bottom by the highest power. Okay, so this is one method, but it's only for polynomial over polynomial. We'll have a couple of different types. Just divide everything by n squared. Okay, well, we'll see that actually this thing is going to converge only because the highest order terms sort of take over. So this will act like, here we have the 5 and the minus 100, and they won't be significant as n goes to infinity. This is going to act like 3n squared over n squared, highest over highest, which is equal to 3. Because you have the same power, same degree, top and bottom, it's going to converge, right? But the precise way of doing this is you divide top and bottom by the highest power. Okay, so this is equal to all right, so here we have 3, here we have 1, and just reduce 5 over n minus 100 over n. These go to 0 because of the n in the denominator. As n goes to infinity, these go to 0. So the whole thing goes to 3 over 1. Okay, really, you could see it by glancing. This is the precise way of doing this, but you could see it by glancing at it from the beginning. Just look at the highest order terms, 3n squared over n squared, and ignore the lower order terms. And you could see that it goes to 3 that way. But this is the way of doing it. Here's another one. You could do, all right. Okay, so that's one type. Okay, we're doing different types. Okay, here's another method. So this method is only used if we have polynomial in n divided by polynomial in n. Okay. Now here's another one. N squared over 2 to the n. Or maybe I'll do e to the n just to make it a little simpler as a first example, as one of the first examples. Instead of 2 to the n, I'll do e to the n. Okay. And now, how do you think we can find, what method can we use, do you think, to do this? Any ideas? Any ideas what method we can use? Something that we did in, actually, I think it was Calc 2 for finding limits. We did x squared over e to the x. Right, exactly, L'Hopital's rule. Remember L'Hopital's rule? L'Hopital's rule, I'll just put it in the box here. Okay, so let's say we're talking about the limit as x goes to infinity, x goes to c of f of x over g of x. Okay, so if f of x goes to 0 and g of x goes to 0, or if f of x goes to infinity. Okay. So if this is true, and you have to have both, everything has to be differentiable. Okay. Okay, so I just read that there. So if this is true, okay, in other words, if top bottom go to 0 or top bottom go to infinity, if you have a 0 over 0 limit or infinity over infinity limit, then this is equal to the limit as x goes to c of f prime over g prime. Okay. So this is L'Hopital. L'Hopital's rule, it's called. So that's what we could do here, because here we have what we call infinity over infinity limit. Top and bottom both go to infinity. In fact, we could have done L'Hopital's rule for the previous example as well. Top went to infinity, bottom went to infinity, so we could have done derivative top and bottom. We could have done that there as well. All right, so here, derivative of top and bottom, since we can use L'Hopital. So this is infinity over infinity, so we can use L'Hopital. So that's how we justify it. We just mention, you have to make sure it's infinity over infinity or 0 over 0 before you do that. So this is justifying using L'Hopital's rule. Okay, so now that we've justified it, go ahead and use it. Derivative of top with respect to n, derivative of bottom is still e to the n. We still have infinity over infinity, so let's do it one more time. So again, justify it. We're going to do L'Hopital again. And we get finally the n on top disappears, so we no longer have infinity over infinity. We can take the limit now. This limit I would call, the top is 2, but I would call it in the category of 1 over infinity. All right, in other words, infinity on the bottom and some number on top. I'm just writing 1 for the general category. So this would be 0. You can think of 1 over infinity as equal to 0. So that's another method we can use, L'Hopital, for these types of limits, infinity or 0 to 0. Okay, so that's a typical L'Hopital, that one. Right, let me see. Okay, maybe just one more. Oops, A sub n. No, so it converges as long as it's a finite number. Okay, converges. All right, and this one too. Only infinity or minus infinity. Okay, so let's do another one. Okay, let's say all right, I'll make log n like this. Okay, n over log n. Okay, so let's do that one. So it's again infinity over infinity. Okay, so justify it. Infinity over infinity, therefore use L'Hopital. Okay. Derivative of top, derivative of the bottom, derivative of ln x is 1 over x. So here we have 1 over n. Okay, and just multiply top and bottom by n. Limit n goes to infinity of n, so that's infinity. So this one diverges. Okay. Okay, so that's again a typical L'Hopital. And there we have an example of something that diverges. Oh, this is an example that I like. Minus 1 to the n. So when n is equal to 0, but let's just write out what it is. When n equals 0, we have 1. When n equals 1, we have minus 1. When n equals 2, we have 1. When n equals 3, we have minus 1. So it depends on if n is even, we get a 1 here. If it's odd, right, it's an alternating, you can call it an alternating sequence because it alternates positive, negative. So that is called an alternating sequence. Question is, converge or diverge? That's the question. What do you think? It's not going to, okay, I said if something goes to infinity, it diverges. That's true. But there are other ways of having something diverge, all right? Not only going to infinity. Okay, as long as it's not zeroing in on a target, think of it like that. Right, exactly, it diverges. As long as it's not zeroing in on a specific number, think about the machine being precise. Would you want a machine that sometimes produces something that's an inch off and every other time, okay, you know, if we speak about n being money, for example, if n is $100, the machine produces something that's 1 inch off. If n is let's say $200, it'll produce something that's 2 inches off. All right, and then it goes back. If it's 300, 1 inch. If it's 400, 2 inches. If it's 500, 1 inch off. If it's 600, it's 2 inches off. Your machine is the machine is going back and forth from producing items that are 1 inch off or 2 inches off in length, let's say. it's certainly not becoming more precise, right? Doesn't matter how much money you spend, you're wasting your money. This machine is not becoming better and better, right? It's sort of, it's still a lousy machine. There's something, some bolt is loose somewhere, right? So it's not, so you're not basically zeroing in on a precise measurement. So that's what's happening here. This 1 minus 1, 1 minus 1. We're not getting closer and closer to a specific number. So it diverges. All right. So we can say a to the n is not going to any L, any limit. It's not zeroing in on anything. So we would say this one does diverge. You understand that? Is that clear? Okay. So that's a nice example that's different. It's not, the limit isn't infinity. Usually when it diverges, it'll be infinity. Okay, oh, can you prove this? Okay, that's a good question. So to prove it, you'd have to use that epsilon definition, really. All right. So you'd have to use that epsilon definition. So let's say we say epsilon equal a half. You know, can you get it within 1/2? Yeah, right. So you just have to prove that the limit doesn't exist. Can we get it within 1/2? Okay, for a specific m. In other words, if n is greater than m, could we get this? Okay, for any L, we'd have to sort of say what L, we have to zero in on L as well. Let's suppose you decide the limit is 0. Okay, so we want to show the limit's not 0. Okay, so let's say if epsilon is equal to a half, then we want to show that for n bigger than some m, a to the n minus 0 in absolute value is going to be less than a half. But a to the n minus 0, that's equal to a to the n, which is always 1, definitely not less than a half. Is there anything we can put in here and get this small? Let's say you say, well, I think it converges to 1. I think L equal 1. Okay. And let's say for epsilon, we want to get it within 1/2 of 1 if n is bigger than some number. Okay, so in other words, we want a to the n minus 1 to always be less than a half. All right. So let's say if a to the n is, if n is even, then we're good. If n is even, then we have 1 minus 1 equals 0. Then a to the n is 1, which is less than a half. Okay, good. That's good. But if n is odd, then we have minus 1 minus 1. That's 2, not less than a half. Okay. All right, so it doesn't matter how big we get. If we take m equal 1,000, doesn't matter. We're always going to have an odd number that's bigger than 1,000, and we won't be able to always make this difference less than a half. Sometimes it'll be 0. It'll toggle between 0 and 2. Doesn't matter what number we choose for L. We can't get this thing to be precise. Okay, so that's how you would prove it, but you have to prove it for a specific value of L, like show that the limit is not 0, or show that the limit is not 1, or show that the limit is not minus 1. So that's what you have to do here. So the epsilon definition, that's what's used to prove that limits don't exist. You know, for this case. All right. But really the best way of thinking about it is this series is not zeroing in on anything, on any number. It's bouncing back and forth, just bouncing back and forth. It's not getting closer and closer to any particular number. That's really the way of thinking about it. All right, so what do we have so far? We have two methods so far for showing convergence. We just have two methods. One is dividing by highest power. That's if we have polynomial over polynomial. And the other method, L'Hopital, to show something converges. We have one other type. Oh, actually, no, that's it. Now I'm thinking of series. That's it. Let me just see if we have anything else. Any other? No, that's it. Okay. All right. So I think we'll continue tomorrow with series. All right. Any questions? All right. Okay. So you have homework up there to do. I'm going to put up. I have to do a Weatherly homework also, which again I always make them short. There'll be at most 3 examples. So I'm gonna pick out some problems. All right. If you have questions, you can ask me. Some people email me questions, and I, mark up whatever they send me, and I send it back. So you can always do that if you want to understand, why you're not getting the right answer or where you're making a mistake. Okay. So have a good day, and we'll see you tomorrow.